to the exhibit forum. We're just about to start the 145 presentation, Static Sign-Off Methodologies, Liberating Functional Verification from Boolean Shackles. If you'd like to join us here for that presentation, we are starting in about 5 to 10 seconds here. Thank you.
Hello, my name is Prakash Narain. Welcome to this forum. I'm the CEO of Real Intent, and we'll be discussing advanced static sign-off methodologies. And let's start with a background on how static sign-off differs from simulation and formal. So first of all, the value proposition of shift left in design verification has taken hold, and we see a continuous progress in that direction. Shift left can be understood as the earliest verification of a design step. And the value of shift left is to reduce the cost of each iteration from within RTL, RTL to netlist, and ECO. And that's why it's gaining traction. The verification methodologies, simulation and formal approaches, they primarily are built on top of Boolean technologies or Boolean engines. And hence they come with their limitations. Formal is inherently has capacity limitations and a very long run times. And simulation starts late and requires a lot of resource investment. And for these reasons, both of these technologies are really not suitable for shift left. What we need is a different approach that will produce results faster. For shift left, we need approaches that will produce results faster and early, and so for that, static sign-off is the best approach to enable that. Now, static sign-off builds custom solutions for specific problems. And as a result, they are can be minimally dependent upon Boolean analysis. And this is how it breaks from the Boolean shackles. So because the static sign-off applications are custom solutions, they can employ abstract reasonings. And the advantages that are provided by this are, first of all, in capacity and performance, where we can run 100 million gate design in a matter of hours, something that formal approaches cannot even imagine to approach. Capacity, where billion gate designs can be analyzed without black boxing. And finally, the customized applications minimize the setup time, the time to set up assertions, and makes users productive with the tools very fast. So for all these reasons and the ease of deployment, static sign-off is the best vehicle driving shift left. So this enables, again, as I mentioned, the blazing performance, capacity, ease of use, ease of setup. These are the reasons why we see static sign-off being used in design flows before simulation and before formal. And today, if you're familiar with traditional static sign-off solutions, the new evolution direction for static sign-off is actually rule-based or command-based functionality. And this is showing up in the next generation of static sign-off products. So if you look at the evolution of static tools, the granddaddy is lint, started 20 years back. CDC, we are all familiar with that. Reset domain crossings, that came after that. Now DFT is finding increased application in design flows. Connectivity checking to make sure the interconnect and architectural integrity of your design is maintained. This is a rule-based application. And now hardware security is again another rule-based application that is the newest static sign-off offering. So Real Intent offers all these solutions, and what I have done is I've requested our team members to highlight the salient features of these to you folks.
Hi, I'm Lisa Piper. RTL linting is a fast and easy way to verify your coding rules. I'm going to share 3 key elements for an advanced RTL linting methodology. The first is to create high-value rules. There you go. So number 1 element is using high-value rules. Let's see how they can improve this RTL. So in this first example, we have a rule to use a system verilog always construct that explicitly defines your intent. By using the always com, we make it clear that the intent is to create combinatorial logic. The next rule checks that when there are multiple sequential conditional assignments that you use the if-else construct. This clarifies that there's only one assign that's going to be applied, which improves readability. Another high-value rule is that output indentation must align with its associated construct. Using proper indentation greatly improves your readability. We can easily see that out1 is assigned in all the branches, making it combinatorial. Element number 2 is multi-policy linting. The rules needed for linting sign-off for different blocks can vary based on, for example, if it's a new block, if it's pre-verified IP, or if it's third-party IP. So being able to do one run with different rules across different blocks saves both runtime and engineering time. Number 3 is targeted debug. To achieve this, group violations by a particular file or a module, or by severity, or by the different kinds of rules. To summarize, advanced linting methodology should include high-value rules, it should include targeted debug, and also efficient multi-policy runs.
Hi, I am Vikas Sachdeva. CDC sign-off involves identifying issues related to metastability, correlation loss, and glitch propagation on clock domain crossings. I will talk about 2 key elements for advanced CDC sign-off. So the first one is glitch analysis. Recently, we have seen a lot of cases where basically RTL level sign-off is complete, but at gate level, you can start seeing glitch issues because synthesis or optimized tool might have optimized differently. And this has become a major challenge. Now, look at this example. At RTL level, output follows the input, so mux is behaving correctly. While at netlist level, synthesis or optimization tool can modify the mux to AND or gates, and this functionality issue can cause glitch problems, which is catastrophic. There are 2 methods to avoid these kind of silicon issues. First, at RTL level, do a CDC sign-off and identify the muxes and mark them do not touch in your synthesis and optimization flows. And second method is do a netlist level CDC sign-off with the glitch rules turned on. The second aspect is dynamic CDC verification. Designers frequently add synchronizers to prevent metastability in their design. But these synchronizers can cause correlation loss at the fan-out when they converge. So dynamic CDC solution, static CDC sign-off must be combined with dynamic CDC verification to ensure there is no correlation loss, to protect synchronizers against metastability stress, and signal path delay skew errors. The way to do that is to run dynamic CDC verification and avoid silicon issues. A complete CDC sign-off approach must include all these methods.
Hi, I'm Sanjay Thatte. I'm going to talk about RDC sign-off. So RDC sign-off exhaustively verifies that signals crossing the reset domains function reliably. I'm going to talk about an advanced RDC sign-off methodology to elaborate on that. Design teams typically tend to use asynchronous resets to reduce power and area. However, that also means that RDC sign-off becomes essential. Let's quickly look at comparison between CDC sign-off and RDC sign-off. First, RDC errors can occur in the same clock domain, which is different from CDC violations that can occur. Second is that RDC sign-off needs complete global verification, whereas CDC errors can be checked by performing local analysis. The number of paths that need to be verified for reset domain crossing sign-off is simply huge. And because of that, performing just structural analysis is not enough. You also need to perform functional analysis. And fourth is the rate of errors that can occur in reset domain crossings is significantly lower and unpredictable compared to those with CDC crossings. Let's quickly look at some of the types of errors that can occur in reset domain crossings. First is metastability. Second is reconvergence of signals that are passing through synchronizers and then causing errors by combining. And third is glitch on an asynchronous reset that can cause functional failures. The noise level in reset domain crossing sign-off can be significantly high. So the solution that you're using can make a significant difference in terms of noise level in the number of violations that are reported. And actually, in some cases, the solution can become simply unusable, or even worse, it can result in missing some errors. A designer can address these issues by defining relationships between key signals through reset scenarios. By doing that, they can reduce the noise level significantly, and it also helps in terms of parallelizing the reset scenarios for analysis and improving performance. Another aspect that is very important for RDC sign-off is debug. It needs to support schematic viewing, violation reporting properly, and also waiving. So all these things become very important, and having good debug support is critical. So an advanced RDC sign-off, in summary, needs to support all these features that we have discussed. It needs to be global. It needs to have structural and functional analysis for quick and effective sign-off. Thank you.
Hi, I'm Kanad Chakraborty. I'm going to talk about DFT static sign-off. Design for testability static sign-off involves checking for DFT-related design bugs that limit the controllability and/or observability of flops and logic. I'll share key metrics when evaluating a DFT static sign-off methodology to improve testability and minimize designer effort. Number one, you need comprehensive rules for async resets, locks, and data connectivity across all design stages. Two examples are rules for sequential depth to non-scan flops and test log reconvergence glitch rules. Number 2, fine-grained rules will reduce noise in violation reports. There should be no overlap between rules. So this example shows two mutually exclusive rules for glitches due to reconvergence versus convergence. Additionally, functional analysis should be judiciously applied to minimize false positives. So no Boolean shackles, we are only judiciously employing functional analysis. For example, when analyzing convergence between two glitch sources, functional analysis shows that there is no reset glitch in this case. The rules should also eliminate reporting duplicate violations for the same error root cause. For example, the precise test log glitch convergence rule shown will only report one error versus multiple errors between every pair of converging glitch sources. Number 3, multiple sets of constraints and rules must be applied to cover all targeted test modes, such as uncompressed, compressed, and at-speed scan tests. Analyzing all test modes in a single run will save several weeks in 3 ways. First, only one setup is needed for all test modes that take hours instead of weeks. Secondly, multi-mode DFT can achieve a much faster runtime of only about 2 minutes per million gates per test mode. And thirdly, multi-mode DFT provides consolidated hierarchical reporting in a single report for maximum efficiency of engineering review and debug. Number 4, grouping violations by root cause will speed up the debug, as it is more efficient to analyze and fix the one root cause versus multiple violation endpoints. Number 5, DFT static sign-off that checks the design with all its DFT constraints for every test mode should be deployed throughout the design process, from early RTL, then after DFT synthesis, and also after place and route. Number 6, a tool that easily plugs into multi-vendor DFT flows lets designers improve test coverage by utilizing the best features across multiple vendors. So in summary, an advanced, mature DFT static sign-off methodology should meet all these important requirements to save engineering effort while eliminating test-rated bug escapes and improving testability and fault coverage. Thank you very much.
Hi, I am Sanjay Thatte. I am going to talk about connectivity verification sign-off. So connectivity verification sign-off exhaustively verifies that specified paths are properly connected and they are not passing through logic that they are not supposed to go through. So I'll discuss key aspects of an advanced connectivity sign-off methodology. First step that is important is that users should be able to create efficient rules and define them very easily. Those rules can be something like you need to have a connection that exists or a connection that does not exist. Typically, to create a set of rules, a good starting point is to create groups of objects. And then these groups of objects can be used to perform connectivity checking directly on them, or they can be used to create custom groups that can be used in subsequent checks. Second important aspect of this is that connectivity verification has to be started very early before synthesis. And by doing this, you can achieve significant benefits. An example of that would be abutment issues that can result in late-stage physical design. And by performing abutment checking at RTL level, you can avoid them proactively. Third aspect is when you're doing connectivity checking, you need to also pay attention to glitches that can occur on asynchronous or untimed paths and cause functional failures. Next, I will talk about comparison of static connectivity verification with formal, simulation, and tickle scripting solutions that may be used in place of that. For formal, the verification is performed exhaustively, but the benefit of static analysis is that it has significant performance benefit, and it can perform gate level, millions of gates in few minutes. And that is a significant advantage compared to formal verification. As far as simulation is concerned, when a rule is defined and connectivity checking is performed, it performs exhaustive verification for that rule. Whereas with simulation, it performs checking only for the test vectors that have been provided while performing simulation. There are certain checks that are possible to be performed only with static checking. In simulation, you cannot perform checking for extra fan-out or for a connection not existing. So that's a severe limitation for simulation. Another thing that is a benefit for static checking is that you don't need any test vectors or test benches, so that static checking can start significantly early, and you don't have to wait for any other things to perform connectivity checking. Compared to tickle scripting, the benefit that static analysis provides is that it can be performed very early. With tickle scripting, you have to wait for post-synthesis netlist to perform checking. And another advantage is that the performance that you can get with static analysis is orders of magnitude better compared to tickle scripting solutions. An advanced connectivity static sign-off methodology depends on various factors. Some of those are efficient rule creation, which static checking allows you to do very easily, performance, ease of use, and debug. By using these factors, you can benefit significantly using static connectivity verification. Thank you.
Hi, I'm Lisa Piper. Hardware security sign-off eliminates security vulnerabilities. A famous security vulnerability example was the Intel Spectre leak. When the prefix data for the path not taken was not cleared, it could be accessed by malicious agents. I'm going to look at 3 types of security hardware checks. Number 1 is data integrity. Designers should ensure that data transfers between the secure domains occur without corruption and without being blocked. In the diagram, the S1 and the S2 are the secure domains. Second is leakage prevention. Engineers should ensure that sensitive data reach unsecure domains where it can be compromised. And third, interference safeguarding is necessary to stop unauthorized data from reaching and interfering with your secure domains. To perform hardware sign-off, engineers must have the flexibility to add their own design-specific rules as well as general rules. Let's compare hardware security sign-off approaches. There's static sign-off and there's also formal. Both are very comprehensive ways of signing off. However, static sign-off can analyze millions of gates in minutes, orders of magnitude greater than formal, and it can handle much larger capacities. A rigorous methodology for hardware security sign-off requires comprehensive analysis, including both user-defined and general rules, and it needs to be fast on very large designs. Thank you.
So that ends our presentation. I thank you all for stopping by, for your attention. And if you want to know more details, a Real Intent booth is on the upper floor. And you're welcome there. We'll be happy to talk to you more. Thank you very much.